Hi everyone. So we are shifting gears a little bit today. We're still talking about limits, but we're going to be talking about limits in terms of something called end behavior, which is basically what happens to your function over time. Like if you run way out to the ends of the graph, if you run way out to the right or way out to the left, where is your graph going? Okay? And so we're going to start without putting a whole lot of like formality on this or formulas or anything like that. And we're just going to talk about the end behavior of these three functions. So starting with this first one, as x approaches infinity, and just to clarify, when I say x approaches infinity, along the x-axis, infinity would be to the right. Okay, that's a terrible looking infinity, but negative infinity would be to the left. So when I say as we're approaching infinity, I'm asking, what is the right side of your graph doing over time? And then negative infinity is what is the left side of your graph doing over time. So, but we can think about it mathematically too. With this first function, if I keep putting in bigger and bigger and bigger values for x, what's happening to the overall function value? Well, it's just going to keep growing, right? Your x's are going to keep getting bigger, so your function value keeps getting bigger. So we would say in this case that the limit as x approaches infinity of f of x is just infinity. This thing is just going to keep growing forever and ever and ever. It's going to keep heading upward. Okay? Just so you know, sometimes when we say limits are infinity, some mathematicians would consider that like the limit doesn't exist, because essentially what we're saying is that there is no limitation, that this is just growing without bound. Okay, is the phrase that you'll hear a lot. So you can write it either way. You can say that, hey, it's heading toward infinity, or you can say that it doesn't really exist because it just keeps growing. But that's the idea, is that this function, as x is getting bigger, everything is just getting bigger. So now let's talk about this one, 3 over x squared. So when you have an x down in the denominator here, and you're making it grow, that means your denominator is growing. So if you think about fractions, as that denominator is growing, your overall values are shrinking. Shrinking, but not necessarily dipping into negative territory, right? If this is a positive 3 up here and I'm putting in bigger and bigger values here, this is never going to turn negative, but it's going to keep getting smaller. And so I would say that in this case, my limit as x approaches infinity of f of x is just 0. Just so you recall, this is a function that you studied back in Algebra 1, maybe some in Algebra 2, but 3 over x squared, that's going to be like one of those side-by-side hyperbolas, so it's going to look like this. And so what we're seeing is that as x gets bigger and bigger, this thing is creeping downward toward the x-axis. That's an asymptote, right? And so that's what we really have going on here, is when we say this limit to infinity is 0, what we've really found is a horizontal asymptote, okay? And it happens to the left as well, but either way, we would say that y equals 0 is a horizontal asymptote. So we're going to get into like how this kind of collides with this asymptote idea later on, but right now we just want to be able to talk about limits to infinity. And so then the third one is sine of x, and sine of x is a really tricky one, because if you think about putting in larger and larger values of x, like really you're just running circles around your unit circle, okay? Or if you think about what the sine function looks like, which might be hard for you to remember, but the sine function basically goes like this, okay? So your function values are just bouncing back and forth forever and ever and ever. They never get bigger, they never get smaller, they're always stuck between -1 and 1. And so this would be a situation where we would just say that the limit doesn't exist at all, okay? Because there's no general trend to this thing over time. It's getting bigger, and then it's getting smaller, and then it's getting bigger, and then it's getting smaller, but it never grows or shrinks dramatically, okay? So this would be a DNE situation for sure. Okay, this is a DNE, but really it's a DNE because it's infinity. This is a true, like, hey, there is no limit here. So what we've kind of looked at here is 3 different functions, and that gives us kind of the three different things that can happen with end behavior, and that's what we're going to talk about with the bullets down here. There's three possible ways that graphs can behave as you run towards infinity. Okay, the first one is that they themselves can go toward infinity, or they can head downward, which would be negative infinity. Okay, so this is like they go up or they go down forever. Okay, and so the kind of the characteristic here is that these are either growing or shrinking without bound. Let me write that, and then I have one other thing to say about that. Okay. The without bound part is important because, for example, this second one we did where the limit we said was 0, that's technically shrinking, right? And it's going to keep shrinking forever and ever and ever. But it's shrinking with a boundary of 0. It never goes past 0. These functions just go straight up or straight down, and they never like change direction or move or anything like that. Okay. So my second possibility is that there's a number involved, right? When I take that limit, I come out to an actual number. 0 is a very common one, but you can get numbers other than 0. And what this indicates when you get a numerical value is that you really have a horizontal asymptote here. And that horizontal asymptote would be at y equals whatever that number happens to be. Okay? Because that's what gives you a horizontal line, is y equals a number. Third possibility is that DNE. Okay? And the one situation I can think of that is always a true DNE is an oscillating function, which is like that sine function. A function that just kind of bounces back and forth and never makes up its mind about where it's going. Okay, there probably are other examples of functions that wouldn't have a limit as we go to infinity. I can't think of any off the top of my head. The trig functions are the big ones to understand that those oscillate, and so they don't have limits to infinity. Okay. Okay. So as far as like what are we going to be focused on today, we have lots of functions that do this. Those are kind of boring, to be entirely honest. Think about your parabolas. Think about your linear functions. Those always just head straight up or straight down. Okay? So there's a lot of these, but they're not very interesting mathematically. These are interesting, but there's not very many of them. Okay? There's only a couple that are going to come out as a true, like, hey, we couldn't find a limit if we tried. And so a lot of our focus today is going to be on these ones that do have a specific limit. They're approaching a number, and then that number gives us an asymptote. So we're going to spend a little more time talking about the limit piece before we get to asymptotes, but that is our main goal for today. Okay. So next up we have what's called the end behavior model. This is a method we're going to use to find those limits as we're approaching infinity. And I'll kind of talk through the steps in just a minute, but let me start with just an example here. So if I gave you the function y equals 3x over x, I hope all of you would look at that and just say, oh, well, that's just equal to 3. And you're not wrong. That is correct. That function is just going to be a boring horizontal line at y equals 3. Okay? But if I were to throw in, let's say, a plus 1, well, that's no longer just equal to 3. Okay, it's going to be like a little bit bigger than 3 because of that plus 1. But what I want you to think about is as this x gets really, really big, I mean like millions and billions, this 1 is going to matter less, right? Like in comparison to how big this number is and comparatively how big this number is, that 1 is going to start to not really matter in the overall value of the function. So this thing is never going to equal 3. But the bigger my x's get, the closer this is going to get to 3, because the bigger my x gets, the less this 1 matters. Okay? And so that's how the end behavior model works. Is basically we only focus on the biggest powers of x. We only focus on these pieces because they're kind of what's in control. And then we say we don't care about the plus 1. Okay? similarly, if I were to give you a function like x cubed plus 2x minus 5 and x to the second minus 3, we'll say. The x cubed is growing way faster than the 2x, okay? Especially once we start putting in really, really large numbers for x. So in the long run, this 2x is not going to be able to keep up with this x cubed. And so this 2x is not really going to matter. And the minus 5 is definitely not going to matter. When we're like taking billions and we're cubing them and we're getting like giant, giant numbers, that minus 5 is so insignificant that it doesn't really change my overall value. So in a problem like this one, I would say I'm only going to focus on the x cubed and the x squared, get rid of all this other stuff, okay? And I'm going to say, what is the behavior of this function? Okay, this function is not equal to what we had to begin with, but if I analyze the behavior of this function, it'll tell me what my original function would be doing, okay? So this function, by the way, if the top is a cube and the bottom is a square, the top is still growing faster. So this is going to be one of those ones that just heads on up to infinity forever. It's just going to keep growing and growing. There wouldn't be a limit here. The limit would just be infinity. It's heading toward infinity. So that's what this is talking about, these 3 steps. So locate the largest degree term. That's what I'm doing here. I'm only focused on the largest x's, okay? Ignore everything else. This is the best kind of math. We can just cross off all the other stuff, okay? Simplify and reduce. You probably don't even have to really reduce all the way. You can probably just tell from what you're left with. But if you needed to mathematically, you could simplify things. I'll show you what I mean by that. And then find the limit of that function. So I can find the limit of this thing that's circled, and it's going to give me the limit of the original function. That's the idea. Okay, so let's try a couple of examples here. So in this first problem, I am only focused on the 5x squared and the 2x squared. All this other stuff I'm going to just ignore because those are my biggest powers of x. And in this case, actually, the x's are going to stay neck and neck. Okay, so if I have 5x squared over 2x squared, the x squareds are essentially equivalent to each other, right? I mean, they are equivalent to each other if that's all I'm looking at. So those are going to cancel themselves out. X squared over x squared cancels. And what you'll have then is this function approaches the value of 5 over 2. Okay. I had a great Desmos graph to show that, but I don't think the way I'm recording this video that I can show it right now. But we'll make sure to talk about that in class, and I'll show you what I mean by this. But what this is really telling me is that I have a horizontal asymptote at 5 over 2. Okay, I could just cancel out those x's and say I'm left with a 5 over 2. Now let's see what happens on this next one. On the next one I'm going to do the same thing. I'm going to focus just on 5x squared, and down here I'll focus on 2x. Okay. Well, the issue with this one is that when I go to simplify these things, my x's don't totally cancel. I'm going to have leftover x's up here on the top of the function. Okay, so if I did take 5x squared over 2x, this would simplify down to 5x over 2. Like I can cancel out 1x. Okay, and so then I would say to myself, what is this function doing over time? And we want to be careful here because this one's asking for a limit to negative infinity. So as I'm putting in negative numbers, like numbers that are further away from 0, further to the left, think about the behavior of this function, okay? It's just going to keep getting more negative. This is one that's going to shrink. It's going to keep heading downward, okay? Well, I guess I should write it to the left, sorry. Because we're talking about what is the function doing to the left. So the left side of the graph is going to overall be doing this. Okay, we don't know if it's curved or straight or whatever, but the trend is going to be the more those numbers are negative, the further this is going to sink to the left. And so I would say that this limit is negative infinity, or we could say that the limit just doesn't exist. Okay, last one. Highest degree on x. This one is actually a little bit tricky because we can't really do highest degree. On the top we can. Hopefully everyone recognizes that it's the 5x we're going to care about. On the bottom, we have to think about which one of these is going to be more in control of what's going on here. Well, the e to the x is going to grow faster than anything, okay? Anything to the power of x is going to grow faster than any quadratic. It's going to grow faster than any linear function. Even if I had like x to the power of 100, ultimately this function is going to beat that, okay? Anything to the power of x, those exponentials just grow so quickly. So this is what I care about, getting rid of that, getting rid of that. And then when I think about what's happening here, if this bottom is bigger than the top, which again, this is going to grow faster than pretty much everything. If the bottom is bigger than the top, that limit is always going to be approaching 0. Okay, feel free to stop there if you need a minute to catch up, or reprocess if you need to watch those examples back. I'm going to jump into a new video and then talk about asymptotes.